Safety. This reaction produces small amounts of sulfur dioxide gas. It is recommended you carry out the synthesis in a fume hood or outside. Chevreul salt is a little-known compound first prepared in 1812 by M.E. Chevreul. What makes Chevreul salt particularly interesting is the fact that it is a mixed valence compound, meaning that it shares a charge over multiple atoms. In this video we will be making Chevreul salt by the reaction of copper-2 sulfate with sodium metabisulphite. In the vial on the left we have 2.4 grams of copper-2 sulfate pentahydrate, and in the vial on the right we have 2 grams of sodium metabisulphite. The copper-2 sulfate is added to 25 milliliters of distilled water and dissolved, giving a solution with a nice sky blue colour due to the presence of copper-2 ions. The sodium metabisulphite is then added to 10 milliliters of distilled water. When sodium metabisulphite dissolves in water, small amounts of sulfur dioxide gas are produced, so it is recommended that you perform this step outside. And now we're going to mix the two solutions together. The sodium metabisulphite solution is poured directly into the copper sulfate solution, yielding a lovely emerald green colour. The green colour is thought to be formed by copper-2 ions, giving a blue colour, and a copper complex that is formed in solution, which has a yellow colour. We're now going to boil the solution to produce our desired product of Chevreul salt. So I have placed the solution on a hot plate and set it for just over 100 degrees Celsius, because we are aiming for the water to boil. I just used a wash bottle there to try and wash off some of the residue on the sides. You can see as it heats up, the colour starts to darken to more of a brown colour, and soon we will see the brick red colour of Chevreul salt start to form. Now I've just turned down the heat a little so the bubbling isn't quite as violent. And if I move the camera, you can see the dark layer of Chevreul salt that is precipitated out of solution and is sitting on the bottom of the beaker. Very dense precipitate, and it falls directly to the bottom. Just let me refocus the camera here. And the exact mechanisms of this reaction are still somewhat unknown. However, it is thought to proceed over several steps. Firstly, sodium metabisulphite is decomposed with heat to produce sodium sulfite and sulfur dioxide. Then sodium sulfite reacts with the copper-2 sulfate and produces copper-2 sulfite and sodium sulfate. The sulfur dioxide then reacts with the copper-2 sulfate to give copper-1 sulfite and sulfur trioxide. As soon as a copper-1 sulfite molecule is formed, a copper-2 sulfite molecule immediately hops on to make copper-1,2 sulfite, our final product of Chevreul salt. Now, something I didn't do in this video, which I should have done and you should do if you try to attempt it yourself, is add boiling chips to the beaker, because as you can see it was bumping quite a lot and the beaker was moving around the hot plate. So you can see I've added a stirring rod and I'm holding the beaker down to stop it from moving around and splashing the liquid everywhere. So a little oversight on my part there. So after running the reaction for about half an hour, this is our final product. You can see we have on the bottom a nice brick red precipitate of copper 1,2 sulfite dihydrate, which is our Chevreul salt, and a slightly greenish blue solution. Now the colour of the solution suggests that I had a slight excess of copper-2 sulfate in the reactants, because if I had stoichiometric amounts then I should end up with a clear solution. You can see we have that lovely brick red colour of the Chevreul salt, which is very unusual for a copper compound. So now to filter the solution and recover our Chevreul salt. So just giving it a quick stir to spread the suspension and into a filter funnel with some filter paper added in. So I'll just let that filter through. Now I'm just going to use a wash bottle with some distilled water in it to wash out the residue that's left in the beaker. So just to quick squirt around the walls of the beaker just to wash down anything stuck on the side. Then add that to what's already in the filter paper. And just one more wash. We want to try and get as much of our product as possible. And here we have our final recovery of copper 1,2 sulphite dihydrate in a vial. And now I'm going to run a couple of tests to show that it is indeed a mixed valence copper compound. So I have a small test tube attached to a ring stand here. Now I'm going to add a small amount of our Chevreul salt to the bottom. And then I'm going to pipette in some dilute 0.5 molar hydrochloric acid. Now the reaction that we're going to see is the red colour of the Chevreul salt disappears, and we see a white precipitate form and fall to the bottom. Now this precipitate is presumed to be copper 1 chloride. Now this test must be done with dilute hydrochloric acid, because concentrated hydrochloric acid will react with the copper 2 ions as well as the copper 1, and you will end up with a green solution of copper 2 chloride as well as the precipitate. So this proves that the compound contains copper 1, as this reaction does not work with copper 2 or any other oxidization states of copper. Just let me focus the camera here, and you can see the white precipitate of copper 1 chloride at the bottom of the test tube there. Now to determine that the compound also contains copper 2. So here we have another fresh test tube. I'm adding another small amount of our Chevreul salt to the bottom. And to this test tube I'm going to add some dilute ammonia solution. And we should see colour change, this lovely deep blue colour. Now what's forming here is a complex, tetraamine copper 2, which is verified to have a blue colour, and this reaction can only occur with copper 2 ions. Ammonia also forms a complex with copper 1, but tetraamine copper 1 complex is colourless. So these two tests have proven that both copper 1 and copper 2 oxidization states are found in the same compound.